Okay, fair warning. If you don't print off your notes, the first page of my notes is fully typed page. Do you see that? Look at your neighbors if it's not yours. I'm not going to wait for you to write all that down. So take a picture of my screen or go back and fill it in later. If you like to write your notes out by hand, that's fine. So just pay attention and understand what we're doing and then fill those pieces in later if that's you. So I want to define for you what it means to talk about Riemann sums, and then we're going to be taking a look at definite integrals in this section. Now, we've seen the word sums before. We looked at them in section 4.2. We had this summation symbol. We talked about this index of summation, starting and stopping in certain values and so forth. So a Riemann sum, it goes like this. We're going to let f be defined on the closed interval AB, and delta is going to be a partition of AB. Partition just means it divides it up. The partition starts at A, ends at B, and we're writing it as x0 to x of n. X of n plus minus 1, sorry. Now, we did that last time. However, our delta partition, delta x sub I, is the width of the ith subinterval. When we looked at the summations for the rectangles in section 4.2, all of those delta x's were the same. The truth is they don't have to be the same for this to work, so this is written very generically, so you see that delta x on the end. However, we saw this notation last time. It was at the very end. We were looking at the left-hand endpoints, the right-hand endpoints, and we wrote it much like this, right? We wrote the summation in front. We went from I equal 1 to 4, because we only had 4 subintervals. And it went from f of x sub I, and it was the first one out until we went to the fourth one in our case. X sub I minus 1 to x sub I with c sub I in the middle is the Riemann sum of f for the partition delta x. Now, you might notice there's no notation in here that says left-hand endpoint, right-hand endpoint, midpoint, right? It doesn't say anything like that. Again, generically speaking, it doesn't really matter which point you let be the height of your rectangle. If the rectangles get infinitely thin, those heights get infinitely close together, and it becomes irrelevant whether it's the left-hand endpoint, right-hand endpoint, midpoint, or something else entirely. So it notes down here that the sums that we saw in section 4.2 are examples of Riemann sums, but these are more general ones. Okay? So let's talk about what a definite integral is then. Maybe it's worth mentioning that what we've done so far in section 4.1 are called indefinite integrals. So these are definite integrals. So if f is defined on the closed interval AB, then the limit of the Riemann sums over the partition delta, and it's notated the limit as delta x goes to 0 of the summation. It's that same summation. This is exactly the same that was on the same thing that was on the previous slide. That's not good. All that's the same thing. The new part's the limit part in the beginning. So what this part at the beginning is saying is that we're going to let these rectangles get infinitely thin, right? The distance or the widths are going to 0. Infinitely thin rectangles, which means there's also infinitely many rectangles. Then f is said to be integrable on AB, and the limit is denoted by the limit as delta x goes to infinity of the summation of I equals 1 to n of f of c sub I delta x sub I. And then we have notation again that we've seen before with a variation. What part of this looks different than what you've seen before? The a and the b. We didn't have those before, right? So when we did not have an a and a b before, this is the same thing. It just means that because there's an a and a b, we're going to have an additional step at the end. This limit is called the definite integral of f from a to b. A is the lower limit of integration, b is the upper limit of integration, which makes sense. It's the lower and the upper on the picture. So picture-wise, we saw a graph. I'll just sketch it in real quick here from what we've seen before, like this last time. Remember that graph? And we said we're going to start at A, and we're going to end at B. And what we're really trying to find is the area under this curve exactly. And what we did in section 4.2 is we did it with 4 rectangles or 6 rectangles or 8 rectangles, but a finite, manageable number of rectangles. And what this is telling us is that we could do it with infinitely many rectangles. And if we did it with infinitely many rectangles, a calculus concept for doing so would be to take this integral, and then we're going to do something with a and b, which we haven't defined yet. But that's what we're looking at, okay? we're going to actually be able to find this exact value, and there's no rectangles involved, and there's no summations involved either. But that's where they're coming from. They're sort of hidden behind the scenes. So here's what we're going to do with our A and our B. One more before we get to that one. It's the next one. Theorem 4.4. If we have continuity, we will be able to find an integral. There are other functions for which we can find integrals as well. But as long as the function is continuous, it's going to be integrable. Okay, we have literally one more thing to do, and then we're going to do a problem. Okay? This is so much writing. I'm so sorry. All right, last one. Okay. This is theorem 4.5. It is the definite integral as the area of a region, all leading up to this. If f is continuous and non-negative on the closed interval AB, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines A and B, that's my picture, is the area which equals from A to B of f of x, the integral from A to B of f of x dx. Okay, so we're still not talking about what we're doing with the A and the B. We're not still defining exactly how the calculus part of this works. That actually shows up in section 4.4, so it'll take it one step further. But this process, whatever it ends up kind of looking like with these integrals and so forth, is going to find this area that we've been trying to do with rectangles in section 4.2. Now, some areas are really easy to find anyway. So, is that one that I want? Yeah. It's the next two that have the areas that are easy to find. We'll get to those in a second. This one is just asking us to set up the notation. Okay, so it says we're going to set up the definite integral that yields the area of the region, and it says we're not supposed to evaluate. So this is the picture that, it's not in your notes if you've got notes printed out, but this is the picture. If you're looking at notes, this is not, we're on page 2 now. And so we're just setting it up, okay? So the setting it up means that we're going to take the integral, and we're going to figure out what the starting point is of the shaded region in terms of x and the ending point. So where does the shading start in terms of x?
0.
Starts at 0. And where does it end?
2.
It ends at 2. And I am missing the equation written on here. The equation of this is y equal x squared. So jot that down if you don't have that written either. I didn't have it written in my slide. Okay, the next part of the definite integral notation says that I'm supposed to have the function notation f of x. Well, I needed the f of x equals x squared to do that. So this is x squared. And then it's dx. Okay, that's all the problem's asking you to do is just set it up. Become comfortable-ish, anyway, with the notation. This is talking about the area under the curve. That's what that script S is meaning for us at the moment. From x equals 0 to x equals 2. It's under the curve x squared down to the x-axis. And remember, the dx on the end is like the bookend for the script S at the beginning. They're either both there or they're neither one there. And that's all we're doing in this problem. Now, on the next two, we're actually going to be able to find the integrals, but we're going to use a geometric formula to do it. I'll warn you right now, and then when it comes to the test, you'll forget, but hopefully somebody will remember. If it says a geometric formula, you have to use a geometric formula. We're going to learn another way to do this problems later. But if it says a geometric formula, you have to use a geometric formula. Now, in order to do that, you need to figure out what in the world this graph would look like. So what does the graph, this is our function, right? What does the graph of f of x equal 4 look like?
It's just a line.
Okay, what kind of a line?
It's a horizontal line.
Horizontal line. Thank you. I was really afraid you were about to say straight. That's what usually people talk to me about. Straight lines. You know, all lines are straight, at least in the Euclidean plane, which is what we're working in. It is a straight line, but it's also a horizontal line at a height of 4, right? So if we're thinking about in terms of this, this is at a height of 4. Okay, everybody good with that? Now I'm going to shade under this curve down to the x-axis, but where will my shading start in terms of x? 0. It says it's going to start at 0. This is 0. And how far to the right am I going to go? To 3. So this will stop here, and it starts here. And you know this shape. What is this shape?
Rectangle.
It's a rectangle. It could be a square, but this one's actually a rectangle, right? Because its height and width are a little different. How do you find the area of a rectangle? Base times height, or length times width, either of those versions. What are the base and the height in this problem? 3 and 4. So the area here is 12. Okay, don't overcomplicate the image. If it's asking you for a geometric formula, it will be a formula that's familiar to you or one that you can easily work with. Okay, we're going to do one more in just a second. Elijah, yes?
12 is the 5 answer 12 or 12 to C?
It's 12. Thank you for asking. There's no plus C's here. Okay, we're actually finding area, which is a quantity, right? It's a numerical value. We'll talk about what happens with the plus C's, though, in section 4.4, because there's actually a very good reason that they're sort of going away. But for the purposes of what we're doing in this section, keep remembering this is an area, and an area is a numerical value. Okay? All right. Same thing. Means the directions are exactly the same. We just need to graph or figure out what the graph of 3x plus 4 looks like. So what does the graph of 3x plus 4 look like? It's also a...
Single line with a slope of 3.
Okay, so it's a line. It has a slope of 3 and a what? It is a polynomial. Generally speaking, this is also a polynomial. What else can you tell me about the line or the polynomial itself, besides the slope of 3, which is important and we need it? The y-intercept is 4. So as I'm drawing this, and your calculator can support you to draw these too if you're wanting to double check yourself, right? The y-intercept being 4 means I'm going to have this as my y-intercept. And then the slope being 3 means I'm going to go right 1 and up 3, right? 3 over 1. How far right am I going? Actually, I'm going to make this a little bit bigger just because my picture will be easier to draw. I'm going to move this over. I realize my scales are not equal at this point, but the picture will be able to be drawn easier. How far am I going to go from left to right? I'm going to go from 0 to 2, right? My limits of integration are 0 and 2, so I'm going to go from 0, that's not 0, 0, 1, and 2 here. And so I need to go, again, up 3 and right 1, and I'd be at something like this. Okay, so this is my line, roughly speaking. And I'm supposed to be finding this area. Do you know what this shape is? It's not a triangle. It's almost a triangle. It's a trapezoid. If you shaded in the part that's on the left, you'd have a triangle, right? But then we'd be moving past the point of 0. We don't want to move past the point of 0. One way of remembering how to find this area is to go back and look up the area of a trapezoid formula. That's fine. So the area of the trapezoid is 1/2, let me draw it this way, base 1 plus base 2 times the height. This is an area of a trapezoid formula. Now, if you didn't want to look that up, or you didn't like that, or you couldn't remember how we decide which one's the bases and the heights and so forth, you can actually change this image into something that's even more easy to work with. If you break it right here, what two shapes do you have? A triangle and a rectangle, right? I know it looks kind of squarish, but it's actually a rectangle. So we could also use it in areas of a triangle and a rectangle formula for this. So let's actually pause right there. This one's a triangle formula, and this one is a rectangle formula. And we will find these 3 different quantities next time and compare them and notice that they're the same.